waiting. I saw that you work with Dr. Federica Bianco. Have you heard about LINEA before?
I'm not sure. I might have heard your name. I don't remember at this point. Did you also work with Federica?
No. It's because we actually work with a lot of us are involved in LSSD, and
sure.
LINEA will become an IDEC. So we're small. Just
are you members of the TVS collaboration or other science collaboration?
I don't think that there is at this moment anyone from the TVS. Most of us are from extragalactic, a solar system, galactic. I would be very interested because I also work with exoplanets, so it's very exciting.
Yeah, that would be cool.
Yeah. So we are a laboratory, so we offer support to researchers and students, and people from different universities, they can be members of LINEA and have access. So we are composed by, I think, 20 institutions or so, members of different places. So just to explain a little bit what LINEA is before we start.
Thanks.
Okay, people are still joining us. It's very nice. I prepared a short introduction based on your webpage, and I will introduce it, and then I will pass you the floor. Okay.
Yeah, thanks.
Okay, so we are already almost 2 minutes past from 2 p.m. So let's start. Just a second. Okay, so hello everyone, and welcome to another talk in our webinar series. This webinar is also being streamed live on YouTube. You can find the link on our website, or you can access it on our YouTube channel, LINEA MCTI. Today we have the honor of having Dr. Somayeh Khakpash from the University of Delaware. In her current research, she develops algorithms to extract features from microlensing light curves and use the features to detect, classify, and characterize the events in fast and efficient ways. Also focus on analyzing light curves of unusual supernovae, creating data-driven templates used in the identification of usual and unusual stellar explosions captured by photometry. Dr. Khakpash is also the coordinator of the Rubin LSST TVS Microlensing subgroup, whose activities provide scientific input to Rubin Observatory to optimize survey strategy regarding microlensing science, as well as ensures the development of community science tools to analyze future LSST microlensing data. She's also a member of the KEL science team. KEL, that stands for Kilo Degree Extreme Little Telescope, a mission surveying transiting exoplanets. Dr. Khakpash, thank you very much for being with us today and for having accepted to give us the webinar on such an exciting topic. The floor is yours.
Thank you so much. Hello, everyone. My name is Somayeh Khakpash. Thank you so much for inviting me. I'm so happy to be here. So today I want to talk about microlensing in the era of two large surveys. So as I just found out, a lot of you are members of LSSD science collaborations. You already know a lot about it. So today I will talk about microlensing in the context of LSSD and the Rubin Space Telescope. So in this talk, So in this talk, I will first talk about what microlensing is, and then I will briefly introduce the Nancy Grace Roman Space Telescope, or shortly Roman. And then I will also briefly talk about the Vera Rubin LSSD. And then I will talk about how these two surveys can be combined for benefits of the microlensing science case. And then I will talk about projects, some of which are my own personal projects, and some of which are projects that we've been working on within the TVS microlensing subgroup. I hope that you will enjoy it. All right, so what is microlensing? In case some of you might not be in this field or might not be familiar with time domain astronomy, I will try to give a clear introduction to what microlensing is. So microlensing is a branch of gravitational lensing. So if you want to describe gravitational lensing, it happens when the light coming from a distant object is lensed by another object in the middle. And then as a result, multiple images of the source, the distant object, will be made on a ring around the lens object. If you look at this image taken by the Hubble telescope, you see a massive galaxy in the middle, and you see a ring of light around it. So this massive galaxy is actually our lens object. And the ring of light is the image of a distant galaxy that has been lensed by this massive galaxy in the middle. So gravitational lensing here, in the gravitational lensing, this ring that you can see here is called the Einstein ring, and the radius of that is related to the mass of the lensing object. So in this case, since the lens is a massive galaxy, the radius of the Einstein ring is larger, and therefore we can resolve the ring with the current telescopes that we have. In the case of microlensing, the objects we're dealing with are much smaller, like stars, compact objects, or even planets. So what happens is that the Einstein radius of the ring will be much smaller, and we won't be able to actually resolve different images by our telescopes. What we see instead is that the brightness of the source will increase as the two objects get closer to each other. So if you look at this animation here, we're assuming that the source, the distant object, is stationary and the lens is moving. In reality, the two objects will be moving relative to each other. So what we see is that the light coming from the distant object will be bent by the gravitational field of the middle object, and then theoretically multiple images will be made. But in reality, what we see, if we check the brightness of the source over time, we see that the brightness increases, it reaches a peak, and then as the two objects move away, the brightness will go back to normal. I also have two more animations that are really useful in understanding what the configuration of this physical phenomenon is. So here we're looking at it from another perspective. So we're looking at the lens plane. Here we're assuming that the lens in the middle is stationary and the source is getting close to it and then moving away. And the green circle is the Einstein ring of the lens. So as the source gets closer to the lens, multiple images of the source will be made around this ring, and the images are stretched along the Einstein ring. So the fact that it's a stretch, it means that the area of the image is increasing, and that's why we're actually receiving more light from the source, and that's why we're seeing that increase in the brightness. So a typical microlensing light curve of a single lens event will be a symmetric curve like this that you see in the lower panel, but in the presence of other effects that I will explain later, this symmetry, this curve will not be symmetric. So we can say that this is like a typical single lens microlensing event. And if the lens happens to have a planet, for example, or if the lens is just a stellar binary system, then the result will be different. In case of a planet, the planet will create an anomaly in the light curve of the source star. So you can see that the planet here is closer to this image. So the planet will distort the image here. And then as a result, what we see is that at that point in time, there will be an anomaly, a small anomaly in the light curve. So looking at this light curve, looking at what time the peak happens, looking at the width of the peak, looking at all these like simple information that we can get from the light curve, we can say something about what's happening physically. But if we want to get the exact parameters of the system, we have to basically model that in more detail. All right, so now that I'm done with like the first part, which is the introduction, I'm going to now talk about the two surveys that I mentioned in the beginning. So first I will talk about Roman, and I will say why Roman is very important for microlensing. Then I will talk about LSSD and what LSSD can do for Roman and what we're doing for these synergies. So Roman is a NASA's space mission, is expected to be launched mid-2020s now. It's the estimation is about 2026, early 2026. Hopefully that won't change. So it's a 2.4 meter telescope, which will look at the galactic bulge in the near infrared. And it has a large field of view, 100 times greater than the field of view of the Hubble telescope. And it will be located at the Earth-Sun L2 point. There are three main scientific goals for Roman. And first, discovering the nature of the dark matter, discovering exoplanets using the microlensing method, and studying far galaxies. So as you can see, microlensing is one of the main goals of the Roman space telescope. That's why it's very important for microlensing. So the microlensing survey of Roman. The microlensing survey will take place during 6 seasons of 72 days long, which are spread along the lifetime of 5 years of the telescope. And it will look at the galactic bulge with a cadence of 15 minutes. So it has a really high cadence in the microlensing survey. And it is estimated that it will observe about 10 to the 8th stars and will discover about 54,000 microlensing events. And it's expected to find about 1,400 exoplanets and about 200 free-floating planets, which is also the exciting part. So why is Roman is important? One of the reasons we're looking at the exoplanets and we're trying to find as many exoplanets as we can, besides trying to find a place like Earth, is also finding out what is the population of the exoplanets. So we want to figure out how the planets were formed, and we have a few planet formation theories that are predicting a specific planet formation. So we want to compare what we detect with what we predict. So far, what we have is mostly planets that are detected from the Kepler mission. So if you look at this plot on the right side, you can see, so the plot is vertical axis is planet mass in Earth mass, and the horizontal axis is semi-major axis in AU. So the red points are planets detected by Kepler, and black points are planets detected by other surveys and using other methods. You can see that most of these detected planets are within 1 AU of their host star. And there is a limit to the planet mass that has been discovered. On the other hand, we have the simulated Roman exoplanets in blue dots. And we can see that Roman is able to find a wide range of planet masses and a lot of planets mostly located at distances larger than 1 AU from their host star. And you can also see that the planets that we have discovered so far, they're not very similar to the planets that we know in our solar system. But Roman is able to find planets that are more similar to our solar system. So we will be able to find out if our solar system is common in the universe. So that's what Roman, that's why Roman is very important for the whole, basically comparing planet populations. All right, so now we come to talk about the LSSD Rubin LSSD. So LSSD is a all-sky ground-based telescope, which is being constructed in Chile, as you probably know. It's going to observe the whole southern sky in 10 years, and it has 4 main science drivers, and probing dark energy and dark matter, taking inventory of the solar system, exploring the transient optical sky, and mapping the Milky Way. So the one that we are focused on for this project is exploring the transient optical sky. That's where Microlensing comes in. So we're talking about like how LSSD can come in use with Roman. So if you think about it, Roman itself is a complete mission. It's focused on finding exoplanets using microlensing. And you might think why Rubin could actually complete that, because Roman itself is planned to have a full microlensing survey. But there are so many different properties that each of these surveys have that they can complete each other. So until a few years ago, Rubin actually didn't have any plan to cover the galactic bulge. And so then it would have been very useful for the microlensing science case. But with the efforts of the TVS microlensing subgroup, the Service Strategy Committee is now considering to include the galactic bulge, which is useful not just for microlensing, but for a lot of other surveys. There are also some limitations to Rubin. It can't provide a high cadence light curve just like Roman does, and it has a limited visibility due to being on Earth. And so considering all of these different properties, we're thinking about how we can use these two surveys together, and what are the tools that we need to develop to basically get the most out of the features of these two telescopes. All right, so here I'm going to briefly talk about the reasons we're talking about the combination of Roman and Rubin. So one of the reasons that Roman and Rubin are important is measuring the satellite parallax. So just imagine Rubin is looking at the sky on Earth, and Roman is looking at the sky from the L2 point of the Sun-Earth orbit. So if they're looking at a microlensing event at the same time, what happens is that, so Rubin is looking at this source star that is going this way, and the lens star is located here. So Rubin will see that the closest approach of the lens and the source is happening at this specific time. And Roman is seeing this event differently. It's seeing that the closest approach is happening at a different time. They also see that the distance of the closest approach for each of these two configurations is different. So what happens is that the light curves that is observed by Roman and Rubin will be different, in that the peak of the event will happen at a different time, and the maximum magnification will also be different. So that's called the satellite parallax, satellite microlensing parallax. And using this, we are able to characterize the lens system. In case of Roman and Rubin, since the separation between them is 0.01 AU, that makes the combination of them ideal for measuring parallaxes of free-floating planets. So free-floating planets are microlensing events that are caused by a single planet that is not bound to any host star. So it's just a single planet, so it's very small, and therefore the Einstein ring is very small. And the separation of Roman Rubin would be ideal for this kind of events. And also consider the fact that free-floating planets will be almost impossible to observe by their direct light. Therefore, we need some alternative methods to characterize those events. So another use of this synergy is measuring the orbital parallax. So the Roman itself on its orbit, it's going to look at a microlensing event, and depending on where on its orbit it is, it will observe the events differently. So this is particularly important for events that are longer. So if the event is it's taking like 10 days, the orbital parallax will not be observed in that. But if the event is taking more than 100 days, then you'll be able to see the orbital parallax effect. So what happens is that depending on the duration of the event and depending on the different factors, what you will see is that the symmetric event that you would have expected to see is now appearing to be asymmetric because of the difference in the location of the observer. So if we only observe with Roman, then if you remember observing seasons of Roman are 72 days. If the event is larger than that, then there's a chance that we missed important parts of the event. But if Rubin is observing Roman's footprint at the time when Roman is not looking, then we'll be able to cover the whole event. And then it will be easier to measure the overall parallax. And another advantage of the synergy is imagine that we have a microlensing event of a wide orbit planetary system. So what happens is that you get a main peak that is caused by the star, and you get an anomaly that is caused by the planet, but the anomaly is separated from the main peak because the planet is separated by a large distance from its closest star. So in this case that you see here, both parts of the event, the main peak and the anomaly, are covered within the Roman's observing seasons. But in a case when the main event is happening at a time when Roman was not looking, we will miss the main event and we will just see the anomaly. We will have no idea if the anomaly was actually an anomaly or if it was just the main event. But if Roman looks at the anomaly in this case, for example, and if Rubin is looking at the sun at the time when Roman is not looking, then even though Rubin has a lower cadence, we'll be still able to see if the main event was happening during the interseasonal gaps. So these are 3 examples of why we talk about Roman and Rubin together. And we also know that Rubin will cover the whole sky over a period of 10 years. And we are arguing that with a reasonable cadence, Rubin itself on its own will be able to give us some estimation of the microlensing event rate within the whole southern sky. So that's also something separate from these 3 that I just mentioned. All right, so here I want to talk about a couple of projects. Some part of these projects are done within the microlensing subgroup that I will talk about, and some parts of that are things that I've been working on. I'm still working on them. So, okay, so within the microlensing subgroup of TVS, what we've been doing so far, you're probably familiar with the same format that you've been doing in other science collaborations. We've been writing white papers since like a few years ago, arguing that the galactic bolt should be covered. And we also argued for a microsurvey or a DDF survey of Roman and Rubin synergy. And we were also working on microlensing metrics that can be used to evaluate Rubin survey strategy simulations to detect and characterize microlensing events. That I will briefly talk about parts of this that has been done in the microlensing subgroup. And we're also providing feedback for the survey strategy committee on the new simulations and how they perform on our metrics. So this project, which its credit goes to Natasha and Marcus in the microlensing subgroup. This is basically the part where we're trying to show how LSSD survey strategy can be designed in order for microlensing to benefit from. So for those of you who might not know, the LSSD survey strategy is not finalized yet. So there are simulations within the LSSD software framework. And these simulations are basically different kinds of designs for survey, for observing strategies. What we do is that we write codes that can evaluate these simulations, and then they can basically they can tell us how well each of these are doing for different aspects of microlensing science days. In this case, we're looking at the detection capabilities of the simulations. So what we do is that we have a set of input microlensing events, like 10,000 of microlensing events that we use as input to the metric. And we distribute the events based on related to the n squared, the number of the stars within each Hill pixel. And then we look at the events who have at least 3 points on the rising side, and we flag that as a detection. And then we count the number of detection compared to the total events. And then you can see that here, the efficiency, which is basically the number of detected events. You can see that for different simulations and then for different time scales. So very short events, 1 to 10 days, or very long events that you can see here. So this work has been also done in the form of basically evaluating the characterization capabilities in the simulations. All right. So now I want to talk about a little bit more generally about detecting and classifying aspects of microlensing light curves and the tools that we are developing for this purpose. So here I have like a set of microlensing light curves with different properties. I didn't get into details of how different the microlensing light curves can be, but depending on the number of the lenses, depending on what the path of the source is within the lens system, depending on the speed of the relative speed of the lens and the source, depending on many factors, we can actually see so many different shapes in the microlensing light curves. So I'm not getting into details of the theory because there's not much time, but basically for each of these events, you have to solve the lens equation, depending on where your lenses are, how many lenses you have, to be able to model each of these light curves. And solving the lens equations for systems with 2 or more lenses can become a very complicated calculation, and it's not always trivial. So I want to argue that fully analyzing each of these light curves would be a time-consuming and challenging task, and it would need a lot of human involvement. So the idea is that when large surveys are releasing their data, that thousands of light curves or thousands of just microlensing light curves, we need methods and tools that can quickly look at the light curves, extract the features, extract the information that you need to start with, and be able to do some preliminary analysis of the light curves. So that's a challenge. And for part of that, I've been working on this specific problem to see if, instead of just analyzing each light curve in detail, which means that to solve the lens equation for each of those light curves and find the best fit function, what can we do instead of that can be much more faster and more efficient? So the solution was to use features that can be extracted from the light curve and then use those as input to machine learning algorithms and classifier and see how effective they can be. So for that purpose, I'm not going to talk about the solution that we've been thinking of for this problem. So we're thinking of, when you look at the light curve and you can see different properties of light curves. For example, you can see when the peak is happening, you can see how high the peak is, you can look at the anomalies and see what they are, like if they're double peak, if they're single peak. And all these different features, if they can be quantified, how effectively they can tell us what kind of event we have. So here I have examples of 6 microlensing events. So the first row is microlensing events caused by single lens events. And the second row is microlensing events caused by double lens events. In the first row, panel A is just a simple single lens model. Panel B is affected by finite source effect, which means that the top of that has been smoothed out. And the reason for that is that the finite area of the source has been comparable to the Einstein ring, and therefore the sharp features in the light curves are smoothed out because the brightness should be integrated across the finite area of the source. And in panel C, you can see an example light curve of a free-floating planet. As I said before, free-floating planets they don't seem to be bound to any host star, and they are acting as a single lens themselves. And since these are really small, their Einstein radius is very small, and therefore the finite area of the source becomes significant compared to their Einstein radius. And then as a result, we see an extremely flat version of a microlensing curve. And then down here, we have events are caused by binary lenses. This panel D is caused by a stellar binary lens, and panel E and F are caused by planetary lenses. So in order to quantify these features that we talked about, for instance, we try to quantify the symmetry of the curve. As I mentioned before, some of the features, some of the second order effects can cause an asymmetry in the curve. So we try to measure the symmetry. And we try to quantify the flatness of the top by fitting the Gaussian distribution. And we also try to find free-floating planet candidates by feeding a trapezoidal function, which is a more extreme flat version of this curve. And we also feed the curves with a Chebyshev polynomial. The Chebyshev polynomial will give us the coefficients of the Chebyshev polynomial will give us a sense of first of all how symmetric the curve is, and also how smooth or how sharp the features in the curve are. And then we have developed this function, this heuristic function, which is a combination of a single lens model plus another function to describe the anomaly. And this function is called a busy function. So the single lens model itself is very cheap to calculate, so that shouldn't be a problem. And we're combining it with another function that is also cheap to calculate, and it would make it easy to extract the information that we need. So just to give you an idea of how these kinds of feature extraction methods work, I'm going to explain one of them, which is my favorite. So this is an algorithm that is trying to extract the planetary parameters in the light curves without actually analyzing the light curve, without feeding the exact model to the light curve. So here we're using a heuristic function, which is called a busy function, and it's been used to fit double peak features into spectra. So we're using this function, we're simplifying it more, and we're adding it to a single lens model. And by doing that, we're able to basically get an estimation of where the anomalies are, how big the anomalies are, and how long the anomalies are taking. And surprisingly, this works really well at finding the basic information about these planetary systems. So the parameters that we're extracting, one of them is the mass ratio of the planet to the star, and one of them is a projected separation between the planet and the star in the units of the Einstein radius. So it's not the absolute separation. And since these are simulated light curves, we are looking at them. We extract the estimation of mass ratio and projected separation, and we compare it with the true values. And we find that for the the separation, we have a very good estimation. And even for the mass ratio, we are able to estimate the mass ratios for most of the events within one order of magnitude, which is very valuable for our purpose. They can tell us what range of mass ratio the event has. And that estimation can also be used as initial guesses when we're doing the final fit for the light curve. So this gives us, each of these algorithms will give us a set of parameters that each of those are quantifying some of those features I talked about. So now the idea is to see if these parameters are actually useful in telling us what we're looking for. So this part has been just started to be tested. So the preliminary results show that depending on what combination of these features we're using, we can get significantly different results, and also depending on what sort of categories we're trying to classify. So here we did some analysis with trying 4 different classifiers on this set of features to classify between 4 different categories. One of them non-microlensing or CV-like light curves, single lens events, stellar binary lens events, and planetary binary lens events. And you can see the result. The result is very close to our expectations, and it's also promising that we can use it as a baseline for further analysis. The rest of the work is ongoing, and that includes adding more non-microlensing light curves to the data set, since we're focused on the Raman footprint and the kind of variability that we're expecting to see in Raman's footprint. We're now trying to simulate the variable stars that are possibly that are expected to be observed by Raman, and that would help us basically increase the category of non-microlensing events. And we're also testing different machine learning structures, including different inputs. So it means that not just using the features, but using the other forms of the light curve itself as input to the machine learning algorithms, which is also an ongoing project. And we are, one of our ultimate goals is to basically be able to evaluate the performance of our machine learning structure for different cadence and see if that would be also applicable for lower cadence light curves. So here I'm at the end of my talk, and I can take questions.
Thank you very much for the very nice presentation. We now have some time for questions. If you joined us on YouTube, please put your questions in the comment section. And if you join us here on Zoom, please raise your hand and ask your question. So questions?
Rodrigo?
Yes, Julie, go ahead.
Hello, hi.
Hello.
Hello, hi, Somayeh. You showed it on the slide explaining the synergy between the telescope and Rubin Observatory and the LSST for the observations at the same time, but at different points of view. Do you have a let's say an estimation of the number of cases that will be observed within this configuration?
So you mean within which configuration? The one that they observe at the same time?
Yes, yes. From both. Yes, when you can have the I don't know. You first observe with the LSST, and then after, I don't know, let's say a few seconds, minutes, you have something seen by the telescope.
Yes, that's yeah. So we have let me just bring, just to make sure. Yeah. You mean this configuration, right?
Yes.
Yeah. So well, I don't have the specific number in mind, but yes, there's this paper by Sadiqa Sajjadian. She has simulated the full microlensing light curve and the event rate in case of different OPSIM simulations. But depending on what the survey strategy will be, they calculated that for the baseline, one of the earlier baselines, when galactic bulge was not covered, and they were estimating that about 100 events in total will be observed with that baseline. But if the baseline changes, that number can become like, I don't remember their estimation in mind right now, but that would significantly change especially if the galactic bulge is included.
Okay. Okay, thanks.
Thank you, Julie. More questions? John, go ahead, please.
Hi, Somayeh. Nice talk. Thank you. My question is, I think on slide 15, you showed simulated events, and some of them were in the SMC or LMC, I think. In those cases, would the lens be in the Milky Way, or would it be all the way out in the clouds? So, like, could you discover extra galactic planets with this?
Yeah, so that's the idea. I mean, it is possible to, with the right cadence, it is possible to look at the planet population of the LMC SMC. So, I mean, that's really an ideal case, but yes, it's possible.
Cool, that's really neat. Thanks.
Thank you, John. Martin, go ahead.
Hi, Somayeh.
Hi,
So
Martin.
you mentioned being able to discover in real time the events for follow-up. So are there like already plans for follow-up of the Broman or Rubin events? Is this with the current network of telescopes for microlensing or with larger telescopes?
So yes, so for both of the surveys, there are plans for follow-ups. The truth is, well, the fact is that not a lot of ground-based telescope will be able to do follow-up for Roman, for instance, right? So it's a set of a very limited set of facilities that can do the follow-up. But I know that it is being thought of, but it's not like 100% planned. And for the Rubin, I know that the discussions are ongoing, but I don't think there is like a final plan, because at this point, we need to basically understand the kind of alerts that will be released, and like how basically effective the alerts can be classified, and all those things that are now being more thought of compared to like just plans for the follow-up observations. That was my understanding.
Thank you.
Thank you, Martin. More questions? Well, I have a question. What is the, when we compare with the LSSD that will have like exposures of 45 seconds or 90 seconds, and I'm not sure now, what will be the exposure time for Raman telescope be?
That's a good question. I don't have that specific exposure time in mind, but their depth, the depth is very close to what Rubin has. So yeah, I don't remember the exact exposure time because yeah, I can double check that, but I don't remember the exact exposure time. But the limiting depth is very close. That's why the two surveys can be worked together.
Oh, yes, it's my question. It's more for me to understand what is the minimum exposure that you need to actually detect them.
For Rubin or for?
Yeah. No, in general, for microlensing, how long does it take? Is the duration of a microlensing event for a planet, that secondary peak that you have in your?
That's a good question. That would really depend on the instrument. I mean, with Rubin, yeah, with Rubin, like the exposure, like a single exposure of 30 seconds does the work. But with other instruments, I need to check. I'm not sure, but yeah.
What is the duration of the event itself? Like
duration of the event?
Yes.
Mm-hmm. So
the part of the planet, not about its starlight.
Yeah, sure. So in general, if you have a single lens event, if the lens is stellar, the duration is between like 10 to 70 days. And in the case of anomalies, anomalies can be as small as, I don't know, 10 minutes or yeah. That's why the 15-minute cadence has been chosen for Roman. Yeah, the anomalies can be very short. We don't really expect to see the anomalies with Rubin. We basically were focusing on characterizing with parallaxes, and also in the case where the main event is missing by Roman, then we're hoping that Rubin can pick that up.
Okay. Thank you. I had another question, but I just forgot it. It will come back. More questions? We still have time. Oh, I remember. Let me ask you. You showed us. It's very interesting, this parallax approach to observe. I assume that it's not possible to know the position of the object that passes in front of the lens. With 3 or more parallaxes, would it be possible to have an idea of the location?
You mean the position of the lens, right?
Yeah, the
Yes.
lens.
Yes. So that really depends on what the lens is, right? Because if so usually most of the lenses in the microlensing survey of Roman will be M-Dorps, and it is possible it will be so hard to see them directly, right? But with other surveys, depending on what the lens was, we've had cases where the lens has been observed separately, and that's easy because you can characterize the lens just by observing it directly.
Oh, thanks. Another last question. Okay, if we have no more questions, I just will ask you, just to give us a quick tip on if someone wants to sign up to the TVS working group, how do we do it?
Sure. So if you look at the TVS website, let me share the link here. On the TVS TVS website, I'm just looking at it. Yeah. So here, I'm gonna put it in the chat. So here, if you look at that on the right, on the right side above, there's this option, become a member. They can click on and you can fill out the form and they will contact you after that. It's fairly easy, and then you'll be just added to the email list and then Slack and everything. Yep.
Okay. Well, thank you.
Sure.
Let me just a final message. So this presentation will be available on our website and on LIneA's YouTube channel. Thank you all for attending, and a special thanks to Dr. Khakpash.
Thank you for inviting me.
Well, thank you very much. Everyone, have a great day. Stay safe, and I hope to see you all again in our next webinar. Thank you very much.
Bye.
Goodbye.
Bye-bye.
Bye.
Bye-bye.